This is one example. Remember this gentleman, action and the reaction. Okay, all of you can see this one, right? Well, let me connect my phone. Otherwise, I will be asking you, disturbing you every time. What is happening here in this photograph that you are seeing? What's happening? Please make it interactive. What's happening here? What is he doing? Where is the action? Where is the reaction? Where is the load? Where is the moment? Where is the lever arm? Quickly. You can be wrong, don't worry, but I need an answer from you. Let me connect to this. In this slide, right, you are seeing this one. Where we will go back to and analyze this for condition of loading and condition of reaction, don't worry. I'm just asking you to think what is happening here. How are you going to analyze this situation? There is some loading, there is some reaction provided by the man, and then there should be some bending, isn't it? If he cannot do bear the weight, it will bend. Or if he is applying more, it will again bend. The member will bend, isn't it? The effect will be either onto the person, onto the member, right? I don't know why you're not interacting more. Anyway, maybe you had your lunch. All of you had your lunch?
No.
Oh God. You must have light lunch before you start in class because it's mid of the afternoon. You should come with light lunch so that you can attend without any hassle or hungry distraction, right? One moment. Right. The contents that I will go through will be starting with definition of what is pure bending. And this module we will only have for beams of all types of cross section, like major types. Say all types will go crazy. Let's start with major types of classification like circular, rectangular, and then square. We will discuss about beams of these three types, and then with symmetric loading. We will not go for symmetric loading, but symmetric loading type. Asymmetric will be followed in your analysis in the higher classes, but not now. We do only symmetric loading and circular, square, or rectangular section of bending types. Okay, let's see this one. And then other types of loading, some types of loading, like what are the types of loading? Quickly, types of loading. So far you learn what are the types of loading? Quick, please. What are the types of loading you can see on a member? Types of loading. You understand what I said? What are the types of loading? Please make it interactive. Then only you are very quick in answering for tests or any quizzes conducted. Types of loading? Simple question. Do you hear me?
Yes, miss.
What are the types of loading you have studied before? No. Point load and distributor load, right? Simply just point load, maybe acting at a point or at the end or at some distance from the support, or distributor load. But sometimes it's a triangular loading, right? These are the types of loading we have studied. So different types of loading also discussed in this class. And then symmetric member in pure bending. We only go for symmetric member, not a symmetric member. What is symmetric member? What is symmetric member? When you cut, the cutting section will yield equal section on both sides. The cross section of geometry will be same. When you cut at any section, it will yield two equal halves on both sides. And then their bending deformation. Uh, you all of you know that whenever there is a loading, it will subject to some kind of deformation. So deformation may be of any type according to the loading type. So we will see what type of deformation, how much deformation. We will also calculate the amount of deformation. Once you know the deformation, the other word is strain, right? The change in the length. One of the word that we use is the strain. So we'll calculate all types of strains here, and then corresponding stress will be calculated, followed by beam section properties. We do stress calculation on stress and also sectional properties. Some of the sectional properties also we will learn how to calculate. Although you have what do you call one moment. Although you have tabular columns, right? You have sections, you have code books to learn about how to calculate these sectional properties. We will introduce here some of the properties that you can calculate. In future, in job place, you will be referring to the tabular columns, right? All of the tabular columns. But here, I will teach you how to calculate those section modulus. The tables and steel tables and the specifications vary from country to country, but not much varying. You can refer to those code books, IS standards, right? IS standards or British standards if you're working in for Imperial, for England or other countries. US, they have ASC codes, American Society for Civil Engineering codes. They have the specifications and the different cross sections. The corresponding properties of the sections will be available. You can directly take from the table. Okay, we will go for section properties, some of the section properties, and then that's example table also will show you how you will refer to when you are going for actual design. Okay, this topic is on design. Okay, a design of the heading is like this. Okay, this topic is on design of the members, structural elements using according to their strength, according to their stress development. Okay, but the main crux of this topic is pure bending, how to calculate the bending in beams, right? Once you know the bending amount, once you know the stress distribution, you can design the member. What do you mean by designing member? I already explained to you. The word designing is referring to what is the size, what is the dimension of the, if you are designing a beam, what is the dimension, cross section of the member, what is the depth, what is the width. You will determine the dimensions once you finish this stress analysis, bending stress analysis. In statics, you determine what is moment of inertia, right? In dynamics, you determine what are the moments and shear forces acting on a member due to a loading. And now in this module, stress analysis, the final stage of analysis is to see how much stress is concentrating, how much stress is distributed in a given cross section due to the given loading and the support condition and the position location of the location in the structure. It will vary. So once you finish calculation of stress, analysis part is over. With this value, you can design your member. Design is referring to dimensions of the elements. It may be cross section, it may be width, depth, diameter, length, and so on. Okay, those things we can do it. That's why you need this. Some of the values you can directly use from the table, and then deformation properties. Some deformation properties, additional one we will teach you to take into account in this design, and some sample calculations. This calculation I will refer to the one we did last time. We already calculated I think 2-3 times the members I introduced in the very beginning of the class to calculate shear force and bending moment. As I said before, the next level is to find the stress. We take the same examples, explore some more to find its stresses, stress distribution in the given member with the given loading and support conditions. Then you will appreciate how the logic of study and logic of analysis is carried out. Lastly, bending of members made of several materials, right? Depending on the material also, it will vary. Just by changing the material property, you can analyze the member for the given condition for its force, moment, and the stresses. Just a recap of what we have done. I already explained, but just quick recap of what we have studied before. You learn about factor of safety. What is factor of safety? What is factor of safety? Forgotten. What do you mean by factor of safety? Please give me the ratio for factor of safety. What's happening? I have to call by name, otherwise Ongzian. What is the definition for factor of safety? Definition for factor of safety. At least you refer and tell me, la. It's not the exam, don't worry. You can refer and tell me what is factor of safety. Then and there you recall what you learn. Ultimate to allowable.
Allowable.
Ultimate to applied, ultimate to design, or the material property to the how much the material can bear, to or over the apply. It can be for load, it can be for stress, right? So in one word, factor of safety is equal to ultimate stress by applied stress, or ultimate load over applied load, or allowable load, or design load. Is this clear? Right? Always the factor should be safety should be higher than 1, because you are designing for safety's purpose. You are designing more than once, at least more than once the property can, the ability of the property, right? And then you did about okay, normal stresses you found with stress strain relationship. You come out with what is yield strength. Forget about this one. This is for more thermodynamics and mechanics. And then stress concentration for the given member we calculated. For the frames, the leads, and the pins we calculated. Some of the questions like what do you call member beam that is loaded with a point load, UDL, right? All we found out. And we also had a modulus, 3 types of modulus: Young's modulus, bulk modulus, and shear modulus, right? For the 3 types of deformation, we had 3 modulus of elasticity. One is modulus of elasticity, another is bulk modulus, lastly modulus of rigidity or shear stress modulus. All the 3 we define, right? We define, and some of the calculation we use the equation. And then strain with the Poisson ratio, right? We determine Poisson ratio, and this one I didn't cover because it is purely on thermodynamics. Don't worry about that. And then some of the stress strain calculations we did using some balls, not exactly these joints. We pin joint. We use pin joints, shafts, right? We calculate strain in the shafts, pin joints, in the wires, right? Wires supported at different conditions. And then we also did lastly shear stress, all about shear stress, shear modulus, polar moment of inertia, angle of twist, all these things we have done. And today, in moment of inertia, this you already studied in your statics. Today we are going to do this beams reactions analysis using purely for the beams. Okay, we are not going for columns. Columns will be the last chapter. We do only for beams by drawing shear force diagram, moment diagram, all these types of analysis. We will do it today. And I go up to superposition method, which is for the combined stress. But let's analyze the very beginning with the tension and compression. Then we'll go for combined stress, which includes also shear stress later on. With that, the topic will be over for bending stress. What is beam? Let's recall what is a beam. Beam can be a simply supported, cantilever, or overhanging, or fixed. There's another one, fixed. Both sides. The same thing is having both sides fixed beam, right? If you see the simply supported, it may be just a beam is kept over. It is like a beam is kept over a support. It might be a pin, using a pin or a hinge, or a pin like this, or a roller, right? It can be for any type. And then cantilever, one end is free, totally free. The other end is fixed. Then it is called cantilever. And then overhanging, again it is supported by a roller, and then some portion is hanging, and another end is pin. Can be any number of pins, but there may be some overhanging portion. And fixed beam is like this. Fixed beam may be what's happening. Fixed support may be both side fixed, completely rigid. Okay, support is both ends are fixed. Alright, we'll have fixed end moments due to load. Okay, beam members. What do you mean by member? Beam member, right? Member that are slender and support loadings slender, right? It is not very big, very thick, right? Generally speaking, they are slender. They support in terms of their longitudinal direction. Okay, the member that are slender and support loadings that are applied perpendicular to their longitudinal axis are called beams. So they bear through the longitudinal axis. So the longitudinal axis is longer than or broader than or higher than the cross section. That is why the cross section is slender. The cross section is slender, but the longitudinal axis, the length should be longer. Then it is called as beam because it is going to support the load borne by the longitudinal axis when there is an applied load perpendicular to the beam, and there is a applied load perpendicular to the beam, perpendicular to the beam, right? And then in general, beams are long, straight bars having a constant cross-sectional area. Mostly it is a regular cross-section, uniform cross-section. Varying cross-section also you can do it. But number one, we have to understand the analysis and behavior of a uniform cross-section. Most likely they are of uniform cross-section and to design. And if there is a change in cross-section, they will design it as a separate member. Right, a continuous member. If you design a continuous member, one after another, you can change the diameter, keep designing according to the load, according to the stress distribution. Because of the applied loadings, beams develop an internal shear force and bending moment that in general vary from point to point along the axis of the beam. Okay, so the loading will vary, right? The loading will be, when the loading is varying, automatically the shear force and bending moment will vary according to that one. In order to properly design a beam, it is therefore become necessary to determine maximum shear and bending moment in the beam. So once the member is loaded, it is subjected to either shear or moment. I will explain clearly about these two in further slides, how this is going to react, how this load is being distributed throughout the member across the cross section. We will see in pictorial view later on. But for now, any member subjected to load will be having a shear subject to a shear force or a moment. One way to do this is to express V and M. For now, the notations are shear force is denoted by V, moment is denoted by M, bending moment. Okay, functions of their arbitrary position x along the beam axis. Moment should be always about an axis, right? It may be or some about a point because you need a lever on, you need a distance. The distance will change the moment value, right? There is a nice video to show how the distance is changing the moment value. I will show you later because I want to cover some of the syllabus. There's a nice video explaining how the moment is varied when the distance is changed, or how important the distance, the lever arm is important in terms of calculation of moments. These shear and moment functions can be then plotted and represented in a graphical way. Shear and bending moment diagram. What is called shear and bending moment diagram, which you know already. In order to formulate the shear force and bending moment in terms of x, we must choose the origin and the positive direction for x. Although the choice is arbitrary, most often the origin is located at the left hand side of the beam and the positive direction is to the right. Okay, it has a procedure to follow. Right, V and M have to be started from one end to proceed to another end. We already done this part. We also calculated shear force bending moment. We also plotted it, right? So we start from one end, having sign convention, having direction convention. We move to another end. With that, you can complete your shear force and bending moment diagram. In general, the internal shear force, shear and moment functions of x will be discontinuous or their slope will be discontinuous at points where a distributed load changes or where concentrated forces or couple moments, moment couple and couple moments are applied, right? Okay, it is not a I mean, when you as you go along the member, right? It may be sometimes there is a pin joint, then it continues with the roller, right? It can be a roller, it can be roller. I put a pin, it can be roller, or suddenly it may be a fixed support, right? Something like this. It keeps changing, right? Or loading also changes. UDL or a point load here, or a reaction moment applied here, there is a moment applied at this point. So like that you have a different types of loading and different types of support conditions along the way. So in all this you have to follow from one end to another, or by using what do you call the principles of superposition that we will explain later. By using principles of superposition you can solve this one by graphically. Okay, we'll see later how this is done. Example of application. See here, this member is like this, right? Originally, this one was here, right? Originally, this one was here. This one is here actually, and this one is going here. So this one is going here because of loading, improper loading, or maybe due to the load, right? The load that is not properly distributed, or the member is not capable, right? The capacity of the member, right? Moment of I mean, the inertia of the member is not good enough to withstand the load that is, this is the load, this is the load. The load that is coming onto the body got broken, right? This is one of the example of bending, already bent. The position should be here, it bent and broken this leg already. The leg is broken already. Bending results in broken condition, right? Collapse or dismantle, get dismantled. Another example, the beginning I asked you, how are you going to relate this picture with your bending example, bending analogy? You can say this is a bending analogy. Any questions so far? The bar carries equal weights. See here, the weightlifter, he's a weightlifter, wrestler we say. When he is lifting up, don't forget about the wrestler, just forget about this part. Wait, open this one. Okay. When you start with this, when you forget about this part, okay, this gentleman, forget about this part in the beginning, right? Originally, there is a bar with so much load on this side, right? How much is the load? About 400 due to gravity will act downward only, right? The first condition, all of you see here, can you see my arrow? Can you see my cursor moving?
Yes, miss.
Yes.
Thank you. So this is the loading and this is the loading. The loading is roughly equal to 400 newtons and 400 newtons. How much kilogram force? Okay, no, I don't go into that part. I hope you understand the conversions, everything, right? 400 newtons and 400 newtons, equal weights, right? Equal weights are there, and it is acting downward due to gravity. When you keep it on floor or lift it or at some height, all will be acting downward. This is a condition of load, right? Overcoming load. And then this gentleman is going to react, right, by holding it. There is a weight coming down. He is going to react or reciprocate the loading at these points. At point 3 from here, at point 3 from here. Clear? He is resisting the load at this point at a distance 0.3 from left and 0.3 from equidistance on both sides. Means what? He is responding, resisting. When the load is acting downward, he is trying to put up, right? Resisting. The resistance is, we can calculate the resistance or reaction to this load. We can calculate the moment cost, we can calculate the stress and the concentration of stress, and also the design. We can do the design, right? In first case, you are seeing the load and the reaction at these points and the distances, right? The same thing when you want to apply only bending, sometimes it is necessary that you apply only bending, right? But then see how your section changed to. The same section can be like this by just applying a moment at this point, moment at this point. How much the moment at this point? Imagine there is a section here. You have the section. You have the section. You have the section at this point, right? If you cut the section, can you hear me? Can you
Yes.
hear me?
Yeah.
What's happening? All right. How do this slide also gone? Okay, I just give the description until this is getting ready. Uh, a member can be either loaded by a load or directly applying the moment. By that, the section design will be changing. In the first case, it was about a length of about, I don't remember the values, but 0.3 on both sides and middle got some values, right? But the same member can be changed to a smaller length with just applying the load, equivalent load at the equivalent moment, the couple moment, moment couple at both ends by calculating the moments caused by the distance and the loading. So this is other way of loading the member or designing the member for this situation of, one moment. Oh, it's restarting like this. Okay. Uh, Depending on the loading condition, it may try to bend or it may cause, it may be balanced. It might be balanced or it may be having some bending as the days and as the number of usages are going on, right? And then next, after giving this example, I want to go for actual derivation of the bending equation. You know what is bending moment, right? You know what is bending moment, what is the equations governing. You already studied in dynamics. Different conditions of support, different conditions of loading can give you standard equations, right? For a simply supported beam with the pointer at the middle, what will be the moment, maximum moment? A typical beam, AB, say AB, with the pointer at the middle, which the ends are simply supported, what will be the value, bending moment value? Point load. I don't know, you are given with the formula sheet when you do the calculation. Please answer me. Are you given with the formula sheet next time? Can you hear me? You can hear me or not? Hello?
Yes.
You are given with the formula sheet, right? Can you give me, but although the formula sheet is given, you are supposed to give the formula, remember the formula, simple formula, so that you can quickly answer. It is not sheet. What is the formula for simply supported? Simply supported. So what is the formula for simply supported? Point load. Say the load is W, the distance is the length of the beam is L. What's the value WL over? What's happening? You these are all That is why I exclusively check whether people have passed this their examinations. Answer me, you remember or not? I just want to be silent in the class, so you're not saying. Hmm? WFA for that I also provided the equation in the beginning, very beginning when we started the class. I think the first one, the stress, understanding of stresses and so on, I have provided. WFA4, right? If it is a UDL, it will be WL squared by 8. Like that, you have standard formulas. I have no time to go through that right now. Please, if I go to the basics again and again, we cannot progress, we cannot move forward. All of you refer to the table, but answer my question. Is it given in the exam, the table was given to you, or you remember the equation and substituted? Equation was given to you? Hmm?
Miss, what equation?
Huh? What
What
equation?
equation?
I asked, one moment, let me open the file. Bending moment and shear force equations like this. See, for example, in this condition, open this true. Let me share this screen. Okay, for different conditions of loading, right? Say for example, there is a beam, right? There's a beam simply supported at its ends and loaded with a W and the length is L. You can write the bending moment value, right? How much is the moment created maximum moment? W, we can derive, but you have standard formula, right? And the same case, same way, same case, if this is changed to UDL, right? W per meter run, right? Then it will be bending maximum bending moment is equal to WL squared by 8. There are standard tables available. I don't know you are given tables or you derive and used it in your exams in engineering dynamics. You are given the table. Let me check if you can have no answer. The examination, where you provided these tables, the equations, how much is the bending for the different types of support and loading condition, or you provided with these equations?
Miss, we did not learn this before.
You did not learn. What do you mean? Dynamics, engineering dynamics. One moment, so shocking to me. One moment, I take the equation. Maybe I take the equation. I take the equation for you. The answer is scaring me. Tantang, can you answer me? Kosar, many others are there, not only Muntasir is always answering. I have to appreciate at the same time I'm sad others are not answering. Wait, I take the table column. Please be frank, no problem. If not, I'll just touch upon the basics so that we can proceed. Normally in my time, I have to remember everything. Otherwise, I remember the derivation. If I forget, I will derive and quickly substitute in the equation. One moment. I take the equation for you. It is having all types of supports and at the end of the textbook also it is available. I think you know you're just hiding or you forgotten. Open. One moment because normally I don't bring it to the class. It is either provided or it is in the textbook itself. One moment. Class slides. If I show you will recall. I wanted to give you in the beginning, but I thought you know already. All textbooks are having at the end of the text. They should have the list of tables. If you go through the along together with the properties they are given. It should be here as well, but it is not here. I take the textbook for you. Sorry, I take 1 more minute, otherwise I give you later. I don't want to waste time here. Let me take the textbook. This is for me to show. Your good old Hiblers. I take the Hibler. Deflections. In the analysis, you're supposed to be getting in your here. In your materials, strength of materials or other books, you should have the table. Okay, let us now to go through that. Give me some time. I will find out for you. Yes. Sorry.
Miss, I sent something in the chat box. You have a look.
Yeah, let me go through. This is the thing I'm telling. Good. The same thing I'm telling. Correct. Give me another same. Are you given this table in the exam last time, or you derive yourself?
I
I'm
don't think
asking
we
the same.
learned before.
You didn't learn. Your dynamics is full of doing this, finding shear force and bending moment. How can you say like this? And the very first class also I derived. Nobody. I mean, you followed or not? The very first class we did some two beam calculations. One moment. Okay, I don't spend time on the. I think you got it what I meant. But there's a tabular column. Normally in the textbooks it is available. Sometimes we give in the because we don't want to test your memorizing power, so we straight away give the equation. I may have to spend time full table, but I have it. In the beginning of the class, I showed to you, but I cannot quickly look at it now. I don't. Thanks, something like this only. I'm telling you have to. Let me share this for everyone. Similar to this only, I'm telling. The one in the chat box. You see here, like this type of whenever when if it is a cantilever, what is the value of moment? What is a fixed means? Both and fixed means with this condition, the moment value is directly given to you. And then what is this? The simply supported. The simply supported WL by 2, right? Because it is what is it? At this point WL by 2, and this side is for full beam, it is WL by 4. And then for what is this one? Different types of loading conditions are given, but I give you the complete table for you to go through. It's better I provide the table for you in this exam, but always advisable for you to have some remembrance of this type of loading, not always referring to the tables. Simple things you can do it yourself. Come on, let's continue with this. I will provide the table like this. Okay, coming here. See, this is changed to moment. 400, when you calculate the moment at this point, right, start from this end. Either you can resolve from left to right or right to left. Okay, at this point means you can come from this to this or this to this. But simple one is go from left to the point it is necessary to calculate. 400 times zero point 0.3, right? So change to moment 120. 4 times, just multiply these two. How much is the value? Quickly, 400 times zero point 0.3 will be 120, right? 120 Newton meter. So the same loading and the distance is changed to moment. Loading and distance changed to moment. Either the beam can be like this or like this. Can be designed with the moment applied at this point. Whichever is safe and stable, we will analyze and then recommend as a final product for the member. This is one of the example, very good example to show you the distribution of load, reaction and the moments. Okay, right. So in this case, this is pure. This member is subjected to pure bending, no load, only subjected to pure bending. That is our topic for study today. What if a member is subjected to pure bending? How the bending stress is distributed across the cross section. Okay, another case, the shear and moment functions must be determined for each region of the beam between any two discontinuous loading. See here, another type of loading. This is a pin, right? It's a pin joint, and there is a triangle load applied at one end. Another end, there is another type of loading at a distance or at the end, is towards the end itself. And then you need to analyze from the here, taking into consideration x1, x2, x3. So this is another type of loading and analysis that one can perform. The corresponding bending moment shear force diagram can be plotted. This example I already explained to you with the numbers also you are seeing here. Thus, pure bending is defined as prismatic members subjected to equal and opposite couples acting in the same longitudinal plane. Acting in the same longitudinal plane. Okay, only one dimensional, right? Above the longitudinal plane. So finally, the value of, the definition of pure bending or moment is known as when the member is subjected to equal and opposite couples acting in the same longitudinal plane. And it is called pure bending. Diagrams can be plotted like this: shear force diagram. Shear force diagram, when the loading is applied, right? When the loading is applied, it will be like this time W running from one end to the X is ranging from this to this. The X can be like this. The X can be, when you analyze in this direction, X is in this direction. This is the origin, with keeping this as origin. From here to here, the X value will be varying and the load will be equivalent to this much. So positive external distributed load like this, and then considering shear force which is acting downward as positive and then upward as negative. Similarly, the moment also you can keep it positive internal moment and then clockwise and depends on the location, whether it's clockwise or anti-clockwise, also you can use it. Shear is obtained by summing of forces perpendicular to the beam axis up to the end of the segment. Okay, when a member is given to you, what you do when this is loaded, the reactions are here, the reactions are here. You start drawing the shear force diagram. Start from here, right? How much is the reaction value, and then moving on. How much is the value at this point? How much is the value at this point? Positive or negative, you will draw something like this, a clear one, right? Bending moment means shear force diagram. And then bending moment also, you will start from one end. If you want to draw the bending moment, if it is simply supported, it should be 0 here, right? It will be 0 here. For a point load, it will be a triangular load, something like this, isn't it? Bending moment, this is shear force. So you will have started from one end, you will move on from left to right. What is the value here? Moving on here, what is the value? What is the value? You will do one by one. And then what else you do? Here, moment is moment diagram also you can draw from one end to another. Note that the sign conventions are opposite when the summing process are carried out with opposite direction. Okay, you have to either consider all upward positive or downward negative in shear force. In moment also you have to consider whether clockwise positive or anti-clockwise negative. All these types of sign convention will be used in roving. For this bending, pure bending, calculation of pure bending, we are going to have like this type of sign convention, positive and negative. This is positive, the reverse is negative. Okay, what are all positive? Let's go through one by one. What are all positive? Okay, number one, you have the distributor load acts upward on the beam. Okay, the distributor load acts upward on the beam. Take it as positive. Okay, the internal shear force causes a clockwise rotation of the beam segment on which it acts. So clockwise is taken positive. Clockwise is taken as positive, right? All upward direction forces are taken as positive. Okay, let it be there. And then the internal moment causes compression in the top fiber of the segment such that it bends the segment so that it holds water like a concave the way wait I draw. So the bending moment like this, if the member bends like this, a concave type, concave here, convex at the bottom, concave, a cup like holding water. You can hold water, that's what I say. Can hold water. This is called hogging moment or positive moment. Hogging. Later I will give you the diagrams. The reverse is positive, negative. If the moment is like this, the bending is like this. Sagging, they call sagging. Okay. This is hogging, this is sagging, this is negative. Okay. Like this. Concave is at the top, bottom, and this is convex is at the top. Here concave is at the bottom top and the convex is at the bottom. So this is hogging, this is sagging moment. Sagging moment. This is taken as negative, this is taken as positive. Okay. In both we will have tension, compression, shear, depending on the condition of loading. That part we will see how to analyze. But in general, bending moment, if the member is, if the in bending moment classification, if the member is bending like this, going inward, then it is called hogging. Going upward, sagging, then treated as negative. Procedure for analysis. Let's move on to the procedure for analysis. Again, you should calculate for the given condition. How do you find the pure bending? Start with calculating doing the free body diagram, then calculate the support reaction, calculate the forces. Forces are loading coming in. Loading, once you know the reactions, you have the loads, you can calculate the moments, and then plot the diagram graphically. Okay, graphically. They will like actually we did 2 or 3 questions in the beginning. I will go back to the question later. But this is the usual procedure of getting your pure bending moment. The next step is pure bending stress, right? I repeat, calculate, do the free body diagram, then do the support reaction, calculate the moments and shear forces acting on it, starting from one end to following the other end, and then plot it by using a graphical representation, taking in one direction. You have to go from one direction. You have to take from just start from origin or one end or one support, go in one direction. You can plot graphically the values positive or negative following the sign convention. You can plot one after another graphically for shear force and bending moment. Finally, generally it is convenient to show shear and moment diagrams below the free body diagram. Better you follow the member. All the diagrams will be drawn below the member. Easy to understand. Symmetric member in bending. Okay, as I said before, we will only follow symmetric member loaded and how the bending moment is caused and the stress distribution is occurring. For pure bending, the internal forces in any cross section are equivalent to a couple, right? And normally in any member it is acting like a couple only. When it goes like this will go like this. Simply sub means not simply sub. Where is it? some distance, like keep it at some distance, then you will have the value. Or take the same example. It will always act like a couple, right? It is not one value. It is a couple. This end will move this direction. This end will move this direction because they are tending to bend the member, break the member. Only when the moment is like this, according to the capacity or ability of the or property of the material, either it will bear or balance, otherwise it will bend at the middle. We'll see how are they and what are the distribution of these stresses, corresponding stresses, which will cause the bending in a while. Okay, I want to derive that bending equation that is most important in your calculations. Let's do the derivation of bending equation. Any question? Give me 1 minute to change to the mode in the to tablet mode. 1 moment. I will change to tablet modes to derive the equation for. We are going to get the table that Tanteng posts in the chart is all equations for bending moment. Okay, fluxural formula for beams or bending. Fluxural means bending moment formula for beams. Now we are going to get the standard equation for bending, pure bending. That equation have many parameters like moment of inertia, the deformation, and then what else? Moment, and then your I value, Y value, A value, all the stresses value, all value, most of them, like about 6 parameters we can determine using this equation. So one has to derive under this section what is the bending formula or bending equation. Let's do that. One moment, let me attend one call, quick one. Attend one call and come back. Uh, any writing pad? Work along with me, derive together with me so that you will also familiar with how this is being developed, equations are developed. This development is holds good for any other conditions. You can derive yourself, but you are here understanding the basics of bending, how the equation, how the unknown can be determined. Where is my? I use the word pattern, easy for me. Any question? All of you take a paper, your class notes. You need to work along with me. Easy for you to remember the concepts. Design. To understand this, to understand how these equations derive, let's see one small demonstration to understand how this is done. Is my video. Chrome is missing.
Is a point beam. Here's my beam again, right? My Nerf noodle.
Okay, are you there? I share this demonstration so that you can follow what we are going to do, right? Just all of you go through this one. I wanted to bring that material, but for left at my home, so I just follow this video. All of you listen, please.
Okay, team, welcome back. We're going to talk today about the beam bending flexure formula. We're going to get a new formula on our formula sheet today. Woohoo! Okay, so what we're talking today about is beam bending. Okay, so if I have my beam, here's my beam again, right? My Nerf noodle. Right? As I start bending this beam, what's happening to that beam? Well, if you can see the top of my beam, I don't know if you can see that or not, there's little wrinkles on it, right? Why are there wrinkles on the top? Because as I bend this, the top fibers of this beam are in compression, right? Whereas the bottom ones down here are being stretched, they're in tension. So somewhere in between the top and the bottom, there has to be something going on. It has to switch from compression to tension, right? Well, it does that at what's called the neutral axis, okay, or the centroidal axis of the part. Here.
Okay. Just go through the. All of you go through the demonstration only. Originally, the beam was straight. When it was applied to a load or a moment at the ends, couple of moments at the ends, it will tend to bend, right? Here we can take the section of a square section. Okay, I'm going to take a square section like this. Okay, let me insert. You're going to derive the flexural formula. All right, flexural formula, flexural equation or bending. A flexure here is referring to bending. Flexural equation or bending equation to derive. Okay, we're going to do that. I'm taking the member, a square member. I just insert using this member, a shape. I take this one, right? Let's take this member of so and so length, right? Length and then the depth. Okay, just showing the cross section of a member, cut section of the member. Once you apply a load, right? Once you apply a load or any type of moment at the ends, it will tend to bend like this. Correct? This is insert. I do again one other one, a line. What will happen to the when it is applied to the load? What will happen to this one? This will tend to bend like this. Oh, it's a straight one. I cannot get right. I just draw by hand. Bear with me for my thing. insert. Okay, let's take this member and then draw the deform section. I put it like this. Okay, just recall the things that are shown in the video. The deform section will be something like this, isn't it? Something like this. It may be like this, gone like this, and then the other end will be like this and like this. Okay, is assumed to be like this. What happened here? The deformation is of two different type. One is elongation, another one is contraction, hogging
Miss, are
type.
you sharing your screen?
Yeah, no.
I cannot see your screen.
One moment, one moment. Can you see now? Can you all see now?
Yes.
Okay. So there is a two different position. This position is like this, and this position turned to like this. This position changed to this position, right? There is a compression here, right? Compression means the contracted. The members are contracted at this point, and this one elongated or extended, right? Extended, right? Originally it was L, now changed to another dimension. We'll see what is happening here by a diagram, right? How to calculate? See, there is a deformation due to a loading, right? Imagine there is a load or moment is acting on it. That has caused the original position from here to another position like this. Let's analyze this member by giving all the parameters and the related formulas. Let's derive the equation. When I take the member separately, when I just take the cross section of the member at any point, then it will look like this. A smaller dimension will be something like this. Originally it was like this, isn't it? Changed to like this, correct? Originally the position was like here. Originally the cross section was square like this. The member was square like this, and then changed to like this. Because this is contracted, this is extended. This position is contracted. One moment, I save this file. Okay. Inner position is contracted at this point. Here contracted. At the bottom it was extended. Alright. Top position was contracted. The bottom portion was extended. Right. Just relate these two because it's a curvature, right? It is not a linear or just a displacement. It's a curvilinear, right? Hence, by using curvilinear formula, you are able to derive the equation for the same. Let's do that derivation. I just complete this circle. I just complete this circle, right? And then I take this to this one. Where is it? Where is it? And there's another one you need to know, the central position. Central position. Just draw it like this. You can all see, right? Let me bigger so that it is easy for you. Okay. So if you take this position, this is a neutral axis, right? Say XX neutral axis. After elongation, it will be, if you this is the neutral axis, and there is a, if you compare this distance, it will be a changing to the new element will be somewhere here, isn't it? The new element will be somewhere here. Let this be y, the change in length. Let the change in length be y. Then you will know what is the value of. See, this deformation we cannot measure directly because it is not linear. It's a curvilinear. By following curvilinear equations, we will find out, or by the formula for finding r, finding length, arc length, finding angle, right? Using that method, we can easily find out how much is the value of this bending stress. Okay, one moment. Let me take the attendance. I forgot to do that. All 13 are here, very good. No, not 13, one person is missing. Who is that? One.
Kalau nggak tahu aku pun trading juga OTFX nih. And 2 minggu lepas aku
Okay, can you all see the Word file? Because I want to use the same notation, I just refer and do it. Let the first axis be AB. I use the same word notation, so easy for us to remember. I use the first section be AB, right? Very touchy now. AB, second section be CD. Okay, the restricted one as a CD. Mark this as C and D. So the distance between them will be Y. Okay, let's mark like this first of all. And then from here, let me refer, otherwise I'll be using something else. One moment. And then moment, direction of moment also we can mark here like this and then like this. Okay, direction of moment, the couple, moment couple I'm drawing. And then you have the center, mark the center, going to center as 0, and then make the angle as, I use the same value, I mark the angle as theta itself, theta or phi you can use it. Let's mark this as theta. And then what are the other dimension need? Let us mark this radius as r. Okay, radius is r itself. And then what is this, another layer, right? This is AB, and I have CD because of the extension. Or take any axis, say for example I use the other color, black, I just use the red. Reference axis like this, and let it be CD, and let this be Y. Okay, the value be Y. Okay, these are all the assumptions that we are making. I repeat once again, we have taken a beam of length L, and say length L, and then applied by the moment, n moments. Because of the moments, it will have bending like this, and the deformed position is shown here. Once this is deformed, then conditions are taken like this. Neutral axis is marked as AB. A distance or any layer, choose any one layer at a distance y, below or above you can take, right? Both are deformed section, right? Here also deformed, here also deformed, above also deformed, bottom also deformed. Let's choose CD as a section below AB or below neutral axis at distance y. Okay, with that you will know how much is the deformation. You really have to imagine, when I say deformation, it's in the circular direction, right? You have to imagine the original and, or find out the difference between original and the new position, right? In this condition we can calculate how much is the deformation and the angle and so on. So what is the angle of, when I say r is the radius, and then the angle as a theta, include angle as a theta, what will be the arc length AB? Can you calculate what is the arc length AB? Anybody? Arc length AB. What will be the arc length AB? I draw it clearly for you. I'm sorry, drawing is not clear to you. One moment. Give me a minute. I will draw clearly for you. I'll just follow exactly the same notation. So when you take from the deformed position, a circle is there, but I take a draw neat circle. Then later I explain. Insert a circle. I take this circle. Hold on, and let me to finish drawing, then I explain where we are. I just take the circle itself, easy for no filling, no fill. Okay, nice circle now. And then radius. I can take the radius. From here I can draw radius. Take this position, take this position. This is theta, this is O. Okay, the origin O. This is theta. Okay, and then the radius R. Okay, radius R. And this is my neutral axis AB. This is my neutral axis AB. Neutral axis at a distance R from the O. And then I choose another section. Okay, I choose another section, say like this, but I draw a bigger one. Choose another section below, which is my CD. Okay, join these two. AB is already there, right? AB is already there. This is your material. This is your material, and this is AB, and then CD. CD is this. Okay, we have three lines. We have three lines. Okay, remember these three lines, then you can answer correctly. Are there any question here? I repeat once again. This is our material. This is the neutral axis. AB is a neutral axis. Okay, neutral axis, or center of the line, center of this one. And then at a distance from the member, or at a distance from the neutral axis, and the my member is finishing somewhere here, but I draw this as well. Okay, the cross section. I take a cross section at a distance y from this position. The depth is taken as y for Adobe. For your clear information, I just take it as bigger one, y. Okay, these are the information. This is the body given to you. So from here to here, A to, from this point to this point is your member. Okay, this point is your member. This continues, the member continues. Member continues. I repeat, this is the neutral axis of the member. Okay, neutral axis not exactly at the middle. One moment. Better to show somewhere here. My member is ending somewhere here. One moment, it's better to have a predefined drawing. So if I say this is a center, it should be equivalently bigger size for all, right? Let me reduce this. I finished the member first. Okay, this is my member. Okay, this is my member. The black one is the neutral axis. Black one is the middle one, and I choose one layer. I use another color. I use one layer like this at a distance y from this position. Okay, now it's clear to you. Can you give me the value of AB? How much the value of AB? Arc length by trigonometry. If radius is this much, okay, if radius is this much r, and the angle is theta, arc length will be, AB will be r theta, isn't it? By trigonometry we can say arc length AB is given by r times the included angle. For any arc, if this is making an angle theta and the radius is r, and this arc length AB can be found by r times the theta. The same thing I'm writing here. Okay, I found the arc length AB. Can we find the similar way the arc length for the next one? This is also arc, right? CD is also an arc, correct? One moment. Why my values are going up and down? Sorry, I'm taking a lot of time. This is exactly the neutral axis is given as AB, and the layer I have chosen as CD. Come on, can you give me CD? Similarly, can you give me for CD? Arc length is given by CD. Arc is given by radius times or distance. Radial distance times the included angle. I use the same included angle because also having an included angle of theta. What would be the value of OC or OD? Anybody? Please see the diagram carefully. Answer me. What would be the distance OC or OD? Come on. Thanks for your patience. I took time to go. Come on. What will be the distance OC or OD? Anyone? Quickly. I draw if you want separate one for you. Our diagram is like this. My angle is this one, CD and CD. This is O, also making an angle theta. And my distance is somewhere here is given as R, right? And from there is Y. What will be the OC? OC or OD? Radial distance will be CD is making an having a radial distance of R plus R plus. Are you there? Can you hear me?
Yes.
Or can you answer me? What is this radial distance? OC or OD? I draw separately here. I want to calculate how much is the CD value. Arc length CD is given by include angle times the distance, radial distance, right? Radial distance is equal to R plus. Why are you not answering? The diagram is not clear to you. See, this is R until this is R, and this distance is Y. Am I right? In the diagram, why can't you answer? So the radial distance made by CD will be R plus Y, correct or not?
Yes.
Okay, let's proceed. Now we found the change in length, right? Change in length, or what is called the final length, that is, or the deformed length of the location. Now let's see another equation from here. What will be the value of strain? How do you define strain? Strain is equal to, come on, how do you define strain value? Strain is equal to, answer me la. Strain is equal to, we are trying to find the deformation, right? Strain is equal to change in length by original length. I don't know why you are keeping quiet. Original length. Original length. What is the time now? We have time. I have to finish this. Right. What is the change in length here? Or original length? The change in length we already found out, right? The change in length is found out already. What is the change in length? Anybody? Change in length for AB? Change in length will be CD minus CB, right? Originally it was AB, neutral axis, but changed to CD, isn't it? C and D. Am I correct? Or I write like this, or draw like this in a AB, right? At neutral axis, the length will be AB. But because of deformation, it is changed to like this. Because of the deformation, it is changed to C. It is changed to CD, isn't it? The location is changed to CD, right? Change to CD. So the change in length can be obtained by calculating the difference between AB and CD, right? So change in length is given by CD minus, a very simple one if you think and answer my question. So strain is change in length is CD minus AB, correct? Original length will be AB itself, right? So the change in length, the extended value at a section CD is CD, value of CD, which is CD minus AB. The change in length to the original length can give me the, the deformed section to the original section can give me the change in length or delta value, delta by L. Say for example, this L is my L is, or R, my original length is R, right? My original length is here is a radial one, so I give it as R itself. Okay. So how much is no, not R, I'm sorry, not R, AB. The value of AB. Value of AB or arc, correct? Okay. How much is this one? Let's calculate this from here. CD minus AB, which is R plus Y times theta minus R theta divided by my AB is equal to R theta. If you simplify, you will end up with, if you simplify, you will end up with the value for strain. Value for strain is given by, can you simplify, R theta minus plus Y theta minus R theta divided by R theta. So it will be cancel Y theta divided by R theta, again cancel, you end up with Y divided by R. Correct? Shall we arrive at strain value? Right? Shall we arrive at strain value? It's better I show the video again, or I hope you can imagine the pipe like this was bent and it has reached a change in position like this. I want to know how much is this deviation, how much is this extension, and how much is this contraction in an average, right? As an average. That is found by finding a strain value. Hence we found the strain value by following the formula for strain, which is change in length to origin length. Origin length was AB, right? Origin length was AB like this. The change in section we have chosen as CD, right? The extended one, we have taken an example. You can take CD or towards the end of the section or above or below any section you can check, because above and below neutral axis the section got changed already. So you can choose section here or here. So I have chosen the section at CD at distance Y to know how much is the change in value or deformed section. And by formula, change in length is to origin length is the formula for the strain. Change in length is given by, okay, change in length is given by CD minus, this is the extended one, right? CD is the extended one minus CB, okay. That's a value. We already found what is AB and CD. I substitute the value to the original is AB. Original neutral axis is AB. Okay. So I got the strain value. From this strain value, we can find other values like stress, then I value and so on. Right? Keep this aside. Then we go for bending stress. Bending stress. Bending stress. What's happening? Okay. Okay. Right. Let's find out the bending stress. What is the formula for bending stress and strain? We got strain, we got stress. Can we relate by modulus of elasticity? Remember, what is modulus of elasticity value? Modulus of elasticity, anybody? Modulus of elasticity is given by stress over strain, or ratio between stress over strain is given by a number. This is after given, the name is given after the scientist Young's modulus, right? It can be Young's modulus of elasticity or modulus of elasticity. It's a number. It means it's a value that is defining stress over strain. Stress over strain, or E is equal to stress over stress. I denote by this one. Strain I denote by this one. Can we now find out the stress? That is our requirement, right? The bending stress sigma can be found by E times strain. How much is our strain? Y over R. Can we now substitute conveniently Y over R? So thus we found the value of bending stress. Is it clear? Any question until now? You really have to imagine. I thought of bringing the tool to understand, make you understand. I repeat once again. Originally, the neutral axis is say L value, 10 meter. Once the moment is applied, change to 12 meter, right? The bottom layer, you choose any distance from the central axis, the bottom layer keep increasing, say 12 meter. Because this number I can find clearly how much is the variation, but in this case it's a curvilinear, right? It's bent like this. I cannot notify how much is the deformation. By using mathematical equation only we can find how much is the value. That's why we have to derive the mathematical equation. We found the strain value, we found the stress value. Next let's find out the equation, bending or fluctual equation. Right, let's recall another set of formula. Okay, take the cross section and just take the small cross section. It's not stable. Okay, let me draw the cross section, then you can understand clearly. When you cut the section here, at this member, when you cut the, what is happening? When you cut so much disturbance. I'm sorry. Okay, when I cut section at this point XX, I will have the cross section like this. Okay, let me do this one. I draw the diagram here. Cross section will be like this because it's a square section. Let us take this to be a cross square section, right? This is the neutral axis. This is the neutral central line or central axis or neutral axis. Say I keep the same name AB, right? And then if you look into the stress distribution of this value, the theta, the sigma, just now we found, the stress distribution will be something like this. Above the neutral axis, it will be like this. All values are like this. All values are like this. And below the neutral axis, it will be away from the member. It will be away, acting outward. So there is a two different direction of stresses acting in the element, above and below. One can notify two type of stresses. That's why you have hogging type, which is compression on top and tension at the bottom. Put together, we can say this is acted upon by a moment called M. Okay, net result or overall result, right? You know that the member is subjected to a compression here and tension here. That's what I'm plotting here. On top member, right above the neutral axis, the member was subjected to inward stress. Below the neutral axis, the member was subject to outward stress. Overall, we can say it is subjected to a moment M. Okay, right. Let's find out how much is the M value. How do you find out? M is equal to, you see here there is a variation between up and down. When you draw the diagram, okay, I do it here. When you draw the diagram from here to here, graphically if you represent, I put the line here. When you graphically represent this point, it is going inward, right? You will have a maximum value here, reducing, right? You will have a maximum value, reducing to 0 at this neutral axis. Moving on, it will be in the other direction, reaching a maximum at the outermost layer, okay? In this direction, and this is in this direction. Compression and tension. This is compression, this is tension. These are neutral axis. Okay. When you plot the distribution of the diagram, right, the stress distribution diagram, you will have like this. Top member will be subjected to compression, bottom will be subjected to tension. How to find out the net value? Because it is distributed between these limits. Okay. See the limits, high big value, right, positive value, to a 0 to another negative value, right? The stress is negative at the bottom, at very high at the bottom. To calculate the overall value, the net value of the stress acting due to this moment, you can integrate by taking an elemental area. Okay, when you take an integrate over the limits or over this area, say if the area of the element is cross-section area of the element is A, integrate over the area and then multiply the value one by one. just take the value one by one. If you take an elemental area dA, right, if you take an elemental area dA, say dA on the diagram, you will have dA times, or dA will be y square, because the square section y. So I will take this cross sectional area as the y square. I'm integrating over the area, so y square into dA. And then what else you have to determine the value? Let's substitute one by one. Alright, I do step by step. You are clear with that? Okay. Bending moment is equal to stress times y times dA. Okay, I write this statement first. Stress times y times dA, right? Bending moment from this formula. From this formula, you have this yr, right? Yr, and then you have m value stated, y times d times a. Okay, proceed with this. I can write what is our stress value. Substitute for stress value will be EYR, EYR, and then there is another y, another dA. I just substitute the value of stress. Okay, you end up with E times R y square dA. This way also you can define it. Okay, either way is okay, just for understanding only. Right, next followed by, please stop me if there is if it is not clear anywhere. I'm just substituting the value, we got it. So after this I proceed with, I use the same notations. We end up with the value m is equal to, what is y square dA? Can we do you remember what is y square dA? Recall your statics, moment of inertia, right? Or square of second moment of area. We can call this as second moment of area, or I write here the name. I don't know why it's not faster. Very laggy. The y square dA, you are squaring, right? Squaring the area. So this name is called second moment of area. Moment of area. We call this a second moment of area, or moment of inertia, or moment of inertia in simple word. Okay, inertia, right? Y square dA. Y dA is the cross sectional area of a member that was deformed to y, and the area is dA. We can integrate and say, but if you square it again, that area, you have y square dA, or second moment of area. The technical term used for second moment of area is called moment of inertia. Let me move on to this one. Okay, I substitute the value of y square dA as I. Right, the good old notation that we are using is the I. Is it clear? I end up with EIR. Alright, can we now substitute for stress value? We got one moment value as EI over R, and if you compare with sigma is equal to EYR, isn't it? Can we substitute the value of stress here? One moment. What is ER here? Can we write down? Wait, I separate this one. This can be, what is ER? Just for convenient purpose, what is ER? Sigma over Y. Am I correct? Sigma over Y. So I just substitute this value. Substitute for ER equal to sigma over Y. I will have the equation M is equal to sigma over Y, and then I. Am I right? Please correct me if I'm wrong. We got another equation in terms of I, right? I and stress. This is what we wanted, right? Bending stress. So I got one equation, I got two equation. Just we can assemble all of them together. I wrote in terms of modulus of elasticity, another one in terms of shear stress. So we end up with shear stress is equal to my over I. That is our ultimate value that we have to determine. This is our ultimate value, bending stress, right? Bending stress, right? From there I can get another equation for you. If y is one moment, what is y here? What is y here? This is AB, right? This is AB. I took a distance of y at CD in the member. When I reach the extent, the complete extent of the member, right? This is the last fiber, end of the fiber, like this one. Earlier we took some distance, right? Earlier we took some distance from the neutral axis, say y. If you reach until this one, it will be y max, okay? It will be y max. For finding y max, just substitute the value, replace y as y max, you will find, right, y as, when you reach until this point, let it be y max, then you will have the value of maximum stress is equal to m y max divided by I. So this is also ultimate stress that one can derive using this formula, bending formula or flexural formula. I'm going to introduce another one value for you. What is I max by y, I by y max? This gentleman. What is this I by y max? Can we replace this one? I by y max, another equation. I by y max is equal to, you can just name this as sectional modulus, okay? Is referring to sectional modulus or S, just simply S, sectional modulus. You can replace a sectional modulus. Sometimes in the equation or in the question it is asked to find sectional modulus. In that case, you treat this ratio as a sectional modulus. You can conveniently find if your sigma's value is there, right? If you are given a sigma value and asked to find the sectional modulus, you can use this formula, m times m over s, right? M over s. Okay, this is another equation we are reaching, I think fourth equation. We found strain, this is 3, eh? This is 3, this is 4. So we got another equation called sigma in terms of sectional modulus. Sectional modulus. We can also write the equation in terms of sectional modulus. Okay, any question so far? And this sectional modulus will vary from I section to I section and then T section and so on. Can we now draw the diagram? Let's draw the diagram. Distribution diagram, stress distribution diagram. Okay, number 1, I section. Let's draw the value of I section. If the member, beam member, like this is the beam, okay? If this is the beam, cut section, say YY, the section YY will have, please imagine, I cannot do the animation here. When you cut, the cut section will show an I section. The cut section can be a T, I, L, right? It can be T, it can be I, it can be L of any type, or just simple rectangle, any type, any cross section it might be, okay? Now, if you take the cross section of I, the distribution of stresses will be like this. I'll show the value here. Starting from, if you draw the distribution of the compression and tension at this point, what will be the value at this point? Can you tell me maximum or 0 here? And what type is it? Imagine the member is loaded, member is loaded like this, and it is subjected to loading like this. What will be the top portion? Is a compression or tension? First of all, answer me. Compression or tension? On top flange member.
Compression.
Very good. It will be
Sorry, miss.
yeah.
I have another meeting now. Can I leave now?
Yeah, you can leave.
Thank you, miss.
So the compression going inward, just put it like this. Is B reducing towards the neutral axis or not? Neutral axis, AB. Will it be reducing to neutral axis or increasing towards neutral axis? Compression. Increasing or reducing? It will be reducing to 0 or the neutral axis. And then what about the loading is here, right? The loading is happening here. So what will happen to the flange below the neutral axis? What will be, is it a compression or nothing happen or tension will happen? Anybody? What will happen to the bottom section? Subjected to? Please answer. It will be subjected to? Hello? It can be a tension member, right? Extended, the member will get extended, elongated, something like this. So this portion is tension, this portion is compression. Right. I don't know why you never answer. Let's go to the T section. Similarly, we will draw for the T section. Okay. T section. Come on, answer me for the T section. I draw the T section here. Let me finish with the T section. Okay. How will it be? Neutral axis, say neutral axis falling here, right? Neutral axis. From the neutral axis I draw. What will happen here? What will happen here? Anybody? Should I call name? Can you answer me what will happen at this point? Imagine there is a loading happening, right? The same cross section you choose, right? What if this is the T section in the second case? What will be the distribution here? First of all, top flange will be subjected to compression or tension due to this loading at this point. Compression or tension? Compression or tension? Answer me, otherwise boring. Only I am talking in the class. Compression or tension due to this loading above neutral axis. Compression. Okay, maximum or minimum? Top flange will be subjected to, I'm talking about the stress distribution. Okay. The top flange will be having maximum. Towards the neutral axis will be 0, isn't it? Subjected to 0. What will happen to the bottom portion? You can do this way or this way also fine. But provided you show different direction, that's important. So it will be a compression type, right? Reducing in the cross section, and the bottom it will be tension going, because it's away from, after a neutral axis is totally further from the loading. That too, the subject member is a slender member, right? The material under which, or material which is subjected to this loading will be smaller compared to this one. That's why you will have this portion is maximum. This will be a little bit, wait, I draw clearly. It will be something like this, smaller, and this will be the bigger one. Okay. Okay, subject to tension, this will be subjected to compression. Okay. I stop here. Any question you can ask me, otherwise we'll continue in the next class. I have next class that in another class continued now. I have to leave. Any question you can ask me. Let me save the file. I don't know why you are not answering. It's so disappointing. You have to be responsive and check whether I'm doing correctly or not, right? The derivation. When I say the cross section, you should be able to imagine. Some simple mathematics, by using simple mathematics, you can solve flexural equation or bending equation. Flexural or bending equation. Bending equation. I stop here. If you have any question, you can ask me. And next class we do some calculations based on that. Derivations are important to understand how you can analyze the member. What if there is a new member given to you in the job place? How to start with? What are the initial assumptions you can make? Right? What are the initial assumptions? What are the boundary conditions you can apply? How do you analyze in 1D? Just I'm doing only one dimensional analysis. You are able to follow them, right? Okay. Where is the team? Team is missing. Okay. Do you have any question? Otherwise, the slide was not shared to you just now. Slide was there, right?
Yes.
Yes, Miss, I can see.
Okay. I was scared. I didn't know it's showing arrow upward. Okay, I stop here. Thank you so much. But all of you go through the text material there in Hibler, the textbook Hibler. It will be very helpful for you to understand and reinforce your knowledge on the topic today, bending, pure bending or bending stresses. Okay, bye.